Hey everyone, welcome to this explainer. I am absolutely thrilled to have you here today. Our goal for this session is simple but, pretty ambitious. We are aiming for a perfect 100 out of 100, total mastery of the subject. To pull that off, we aren't just going to sit here and memorize formulas. We're going to completely master the fundamental why and how of polynomials. So if you've ever felt even a little bit intimidated by algebra, seriously, don't worry. By the time we wrap up this explainer, you are going to see exactly how these mathematical structures work, literally from the ground up. Okay, let's dive into this. Here is our roadmap for today. We'll start by laying down the basic building blocks, then figure out how to identify true polynomials, classify by degree and terms, learn the secret to finding polynomial zeros, and finally, we'll be visualizing zeros on graphs. Math is totally cumulative, so we are building our knowledge block by block today.
All right, Section 1, the basic building blocks. Let's look at the absolute smallest ingredients of algebra.
Think of our primary algebraic ingredients kind of like a baking recipe. First, you have constants. These are fixed values, like the number 2 or pi. 2 cups of flour is always 2 cups of flour, right? It never changes. Then you have variables, like x, y, or z. These guys shift and change depending on the specific problem you're looking at, much like swapping out the toppings on a pizza to suit whoever is eating it. Now, when we take those raw ingredients, our constants and variables, and mix them all together using basic operations like x minus 4 or x times y, we create what's called an algebraic expression. It's essentially the raw dough of math. But as you know, not all dough turns into a perfect loaf of bread. In the same way, not all expressions actually get to be called polynomials. Moving right along to Section 2, identifying true polynomials. Let's talk about the strict rule that turns a basic expression into the real deal. Take a second to read this golden rule. All polynomials are algebraic expressions, but all algebraic expressions are not polynomials. It creates a bit of a mystery, doesn't it? It basically tells us right off the bat that there are expressions out there that are just imposters. They're posing as polynomials, and we need a reliable filter to figure out which is which. So, what's really interesting about this slide is the strict rule we use to filter out those imposters. Here it is. The variable's power, its exponent, absolutely must be a whole number. That means 0, 1, 2, 3, and so on. Notice the examples we have. The expression x squared minus 1 has a power of 2, right? 2 is a whole number, so it's in. But look at t to the power of negative 1. Negative 1 isn't a whole number, so no way it is instantly disqualified. All right, let's put this to the test with a question pulled straight from Daily Practice Problem 1. We have the expression 3 divided by x. Based on the golden rule we just covered, is this a true polynomial? Take a second and lock in your mental guess. Well, the answer is a resounding no. Why? Because you always have to beware of hidden negative powers. Mathematically speaking, having an x trapped down in the denominator is identical to saying x to the power of negative 1. The big trick here is that you must always simplify the expression first. That exposes any of those hidden rule breakers. Okay, on to Section 3, classifying by degree and terms. Let's organize our verified polynomials into neat specific categories. First up, we can classify them by simply counting the terms. Think of terms as the chunks of the expression, which are separated by plus or minus signs. If there's only one chunk, like an x, or just a constant like 2, it's a monomial. Got 2 chunks, like x minus 1? That's a binomial. And if there are 3 chunks, like x squared minus x plus 1, you guessed it, it's a trinomial. It is literally as simple as counting 1, 2, 3. And this brilliantly illustrates our second method, classification by degree. Now, the degree is just the absolute highest power of the variable present in the polynomial. If the highest power is a 1, we call it linear, because its graph makes a straight line. If the highest power is a 2, it's quadratic, which gives us that beautiful U-shaped parabola. Highest power is 3, that's a cubic polynomial. The degree is basically the captain of the ship. It entirely dictates the geometric shape of the math. So let's put it all together, kind of like giving each polynomial a first and last scientific name. Walking through these examples from the notes. Take 5x squared minus 3x plus 1. The highest power is 2, so its first name is quadratic. It has 3 distinct chunks, so its last name is trinomial. Put them together, quadratic trinomial. Next one, x cubed minus root 2x. The highest power is 3, making it cubic. 2 chunks makes it a binomial, so its exact full name is a cubic binomial. Makes sense, right? Now, before we move on, you absolutely need to know these fun, surprising special cases so you don't get tripped up on an exam. If you just have a raw number floating by itself like a 2 or a pi, that is called a constant polynomial, and its degree is always exactly 0. But, and this is the kicker, if you have the number 0 itself, it is known as the zero polynomial, and its degree, well, mathematically, it's actually not defined. Seriously, lock that away in your memory. Exam writers absolutely love to test that specific fact.
Which brings us to the action phase of the explainer, Section 4, Finding Polynomial Zeros. How do we actually solve these things?
The procedure here is actually remarkably straightforward. Finding a zero, which is sometimes called a root or a solution, they all mean the exact same thing, just means you are hunting for the specific x value that completely destroys the entire equation, balancing it out to exactly 0. Step 1, you set the polynomial, p of x, directly equal to 0. Step 2, you use your basic algebra skills to isolate and solve for that missing x. Let's actually apply this. Say we have p of x equals 3x minus 3. Set that whole thing to 0. We move the 3 over to the other side, divide by 3, and boom, we find x equals 1. And to prove it, if we substitute that 1 back in, 3 times 1 minus 3 is 0. It perfectly balances out the equation. That makes 1 our official 0. All right, final stretch. Section 5, Visualizing Zeros on Graphs. This is where we translate all this abstract algebra into real-world geometry. So, the crucial point here is that a zero isn't just some abstract math on a piece of paper. It's a physical location. When plotted out, the zero represents the exact collision point where your graph line cuts right across the horizontal x-axis. Whenever y is 0, whatever your x value happens to be at that precise intersection, that is your root. Because of this amazing geometric rule, finding the number of zeros is literally as easy as just using your eyes. You don't have to do any complex calculations. Look at the left side. We see the squiggly line crossing the horizontal x-axis exactly 3 times, so it has 3 zeros. On the right, the wave dips and rises across that axis 5 times, giving us exactly 5 zeros. You just count the intersections. Let's throw one last test your way, straight from the real CBSE 2023 exam to prove you've got this down. Based on the intersection rule we just covered, how many zeros does this downward-facing parabola have? Take a close look at where it interacts with that horizontal line. Let's move to the next slide and see how this builds. The answer is exactly 1. The curve sweeps up, kisses the x-axis at a single, precise point, and drops right back down. One contact point means 1 0. If you spotted that instantly, you have absolutely mastered reading polynomial graphs. Bringing it all together, we have this mastermind map summarizing our entire journey. We started with tiny variables, organized them by degrees and chunks, and finally plotted their zeros onto complex graphs. Seeing exactly how all these individual pieces connect is the real secret to scoring that perfect 100 out of 100. We've seen how easily we can spot 1, 2, or even 3 zeros on a simple graph, right? But consider this provocative thought as we wrap up today. If the degree dictates the shape, and a cubic polynomial with a power of 3 creates those nice curving waves, what incredibly wild, complex geometric shapes are hiding in polynomials with 100 zeros? What does a variable to the power of 100 actually look like out there in the universe? Keep that infinite algebraic possibility in your mind and let it fuel your curiosity as you step into more advanced math. Thank you so much for joining me for this explainer today.